So, what is variable control charts and why do we need it? So far, for the last 2, 3 weeks, we have been talking about statistics, and we know how to analyze data, a scientific data, a group of data by calculating the central tendency and dispersion of that data group. And we said that those are the two most critically important parameters to understand the characteristic of the data. It's the easiest way to make sense out of a group of data. But it is not always enough, or it doesn't give the whole picture, especially in a continuous processes, which is very common in engineering. In engineering, the data is usually not static. It changes and it's produced over a period of time. So if you have a static data that you collect at one point in time, yes, it makes sense to study that data by just calculating the mean value, right? And the dispersion of that data. But again, in engineering, we create data over a period of time, and that data is changing continuously. So instead of creating a static data, how do we create a dynamic data that changes over time? If we collect the data and we distribute them over a chart that also shows the time that the data is collected, the data can look like something like this. So from this data to a different distribution of data. Actually, this is not a distribution, but this is how it looks like if you distribute the data over a period of time. So for example, probably this data is representing this one. Maybe this data is representing this one, and this one is representing that one. When you look at that data group, of course, this is the same data group, you can easily analyze the dispersion and the central tendency. But when you distribute or when you present, when that value is created, when that value is collected, now you have a timeline, and you can see that up to that point in time, everything looks random. The point values are going up and down, randomly changing, but after that time, all the data points started decreasing. So this is a very significant pattern that you need to identify. This pattern value is not represented in that static data. It doesn't tell you what happened at that point in time. It's a new information. You didn't have that information before by just looking at the distribution of the data, but when you place that same data values on a timeline, now it's very clear that there is a pattern in that data, and that data values are decreasing. 1, 2, 3, 4, 5, 6, 7, 8 data points consecutively decreasing. So I can definitely interpret it in a way that something changed at that point in time, and the data values started decreasing. And I can focus my efforts on the reason why the data points started decreasing. That is the basic fundamental understanding and the reason why we have variable control charts, that we would like to see the changes of the data points or data values by time. I hope this makes it clear why in engineering we want to see also the time that the data values are created or collected. So what is the variable control chart? A variable control chart is a systematic and more organized way of representing the same data that I just tried to present here, its central tendency, its dispersion, and its value in time. And those variable control charts are also going to help us to analyze if the process is under control or not. So the function and the significance of the variable control charts, we said that, yeah, the most important characteristic or the benefit of using a control charts, they show the source of the problem. This word, of course, is it's not easy. It doesn't really directly shows you the source of the problem, but since it tells you at what point in time the problem happened or something significant happened, what we can do is easily we can go back in time to that specific time in history, in records, and we can analyze what changed at that time. For example, if it's a production line, you can go back to that point in time and see if the operator has replaced, the operator has changed, or a new material uh, came to the production line, or a new setup maybe is made. So those are the things probably usually causes changes in the values of the data that we collect. So you can easily, by looking at your historic data, you can go back to that point in time and you can look for what caused that problem or what caused that change in the characteristics of the process. So that's the most important, significant feature of the variable control charts. What happened and when happened that changed. As you see here, the major point is the data is varying, right? Data here is decreasing, same, decreasing, increasing, decreasing, increasing, increasing. But what we obviously see is the main characteristic of the data is change. The data is change. If that change is random and in the uh, in the nature of the process, it's an acceptable change. By the way, we accept it. We know that the change is gonna happen. No two data values in engineering or in science can be perfectly same because of the inherent uh, characteristics of the processes, the tools, the equipment, the processes, the machines, the operators, the material that we use. There will always be some changes, but the level of changes and its randomness depends on the process. So we accept that there's going to be a variation, but as long as it's in an acceptable level, we will be able to go with that level of variation. If the variation is as significant as this one, as you see here, there's a pattern. If it's as significant as this one, then we will have to stop what we are doing and look for the source of that problem. So variation is gonna happen. You cannot escape from that. You have to accept it. But what kind of variations can we observe in a process? There can be variation within a piece in production, for example. Think about the hood of a car. It's a big piece, you paint it, and maybe there might be some paint or tone changes, color changes on that piece. So you can easily analyze the changes of colors on a single piece, and this is considered to be a variation within a piece. Or let's consider a fast running production line. For example, you're producing screws, bolts, nuts. Probably takes less than a second to produce one bolt or a nut. And you want to analyze the specifications, let's say dimensional specifications, the outer diameter of a bolt, and you start measuring them. And in this case, the variation that you're analyzing is piece to piece variation. Or in a different situation, for example, you come to the production line in the morning and you collect a sample of data in the morning. You analyze it, you calculate the central tendency, you calculate the dispersion, and then afternoon you come back and you again collect another sample and you compare them. Now this is a study, this is an analysis that we can call time to time variation. So you're looking for the variation that changes over the time. These are the three fundamental ways of looking at the variation: within piece variation, piece to piece variation, and time to time variations. In terms of the variation and their causes, now this point is very critical. We have to understand that some variations are acceptable. We cannot run away from variations, but what kind of variation is unacceptable? What kind of variations should signal us something that needs our attention? All right, so chance or common causes, which are small random changes in the process that cannot be avoided. Those are the variations. We accept them. We try to live with them. We try to survive with them. As I said before, the machines, the equipment, the systems that we use, they are not perfect. Even if you go and buy the most perfect, let's say, milling center, $1 million milling center that can run with a 10 thousandths of an inch precision. But as you see, it is only capable of producing to the precision of 10 thousandths of an inch. If you want, or if you measure the parts or pieces produced with that machine, and if you're capable of measuring 100 thousandths of resolution, you're going to see variations. Now, are those variations important? Are they critical? And is there any way to prevent it? Now, you're assuming that the machine is perfect, it's running in an ordinary state, and if the variations doesn't show any pattern, then you have to assume that the production is in control and the variations are small, and probably they are caused by chances. They are caused by the inherent characteristics of that system, of that machine. Uh, but on the other case, as I mentioned before, if there is a certain specific pattern that you can identify in the process, and if it can be attributed to a certain change in the system, maybe a change in the material, setup, machine, operator, environment, or something else, and causes a pattern, a new pattern in the process, then those are the assignable causes, the causes that can be prevented, the causes that can be changed, the causes that can be fixed. And those are the ones that we are interested in. We try to identify them and we try to eliminate them. Those are the ones that can be easily identified and easily prevented. Common causes, can we prevent them? Yes, but preventing the common causes is usually difficult, and it usually requires bigger, larger investments. As I mentioned before, if you buy $1 million equipment, it will still have some level of variation in it. And how do we eliminate that variation? By probably training on the operator side or purchasing even more expensive equipment. So it's not something that you can easily identify and fix. You have to do system-wide changes, and they are usually done by the management, by the administration, and you can only eliminate them by completely changing the system. They are not easy to identify. So again, one more time, what we are looking at is the changes that causes a certain pattern on the process, and they can be assigned to a certain cause, certain problem, and we can easily identify by looking at the variable control charts. So those are the ones that we are interested in quality control. So what are those parameters again? If you have taken any manufacturing courses, this picture is a very simple picture, and that is presenting a manufacturing process. You're creating a pocket probably here. And what are the parameters that can cause any assignable cause here? Let's consider them. Let's first focus on the cutting tool. The cutting tool size, cutting tool shape, cutting tool material, right? These are the parameters that can cause any changes in the process. Also, if we concentrate on the material that we are cutting, the type of the material, right? And the setup that is holding it, and the machine spindle speed, feed rate, and if you're using a cutting fluid or not, chip removal systems, those are all parameters that can contribute to the changes in the system, and that they can cause significant variations in the final product, which are assignable causes. All right. So even creating a simple packet on a part, we can identify numerous number of reasons that can cause assignable problems. So what is a control chart, variable control chart? This is a typical variable control chart. And I'm going to try to quickly explain it, and then we'll go into the formula, how to create a variable control chart. But first, I want to explain what's happening on that chart, what those points are representing, and what these lines are, what do they mean with respect to those points. So how does it happen in engineering? The most common application area of variable control charts in engineering is in a production line. In a typical production line, let's say you are a car manufacturer, there are probably hundreds of points that you collect data. You collect quality data. And how does it happen is the quality engineer goes to the plant floor, let's say, to that specific area that he needs to or she needs to collect data. And that person collects a sample, a group of data, let's say 10 individual readings, 10 observations. Let's make it simple and let's make it easy to picture in our minds. Let's say you are in the morning, you're going to the plant floor and you are collecting 10 screws, all right? And then you measure their ODs, outer diameters, 10 screws in the morning, all right? And what you're gonna do is you're gonna collect that data, you're gonna read that data, and you're gonna record them. And this next thing you're gonna do with the data is you're gonna calculate their average. The average is gonna be represented by X bar, right? Each unique reading can be represented as x1, x2, x3, x10. Those are individual data points that you collected in the morning, the first time you went to the plant floor. And then from those 10 values, you calculate their average, x bar. Since this is our first subgroup or sample, we can call its average as x1 bar. All right. You also calculate the dispersion. As you remember, the way that we calculate dispersion can happen in two ways. You can either calculate the standard deviation of that subgroup or the range of that subgroup. All right. So you have to do either one of them, standard deviation or the range. Then what happens? Maybe a few hours later, you come back and create another subgroup. Again, you collect equal number of samples, 10. You collect x1, x2, x3. Those are individual readings from the screws that you're collecting. And then what happens? Again, you calculate their averages. This time we call that x bar 2, because this is my second subgroup. And again, for that second subgroup, you collect and you calculate either their standard deviation or its range. Then a few hours later, usually those periods between each collection has to be equal to be consistent. Again, you create another subgroup by collecting equal number of individual readings, individual screws. Again, you collect 10 screws, you do measurements on them, you calculate their average. In this case, we call it x bar 3. This is the third subgroup. And again, we calculate either standard deviation or the range. And how many times do we do that? 20 times typical. It can be more if it's a fast running and let's say it's a year-long production. You will probably do maybe 30, 40 subgroups. All right. How many? So then, what do we do with those data? So what we need to concentrate here is subgroup averages and either the standard deviation or range. This specific variable control chart is, as you see from its name, it's an X bar chart. So what does it mean? What does an X bar chart means? The points that you see here, they represent X bars. So they represent subgroup averages. So they are these values. I have X1 bar, I have X bar 2, I have X bar 3, but as we know, it continues. Maybe 20, maybe 30 subgroups you create. So let's see how many subgroups that specific variable control chart has. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So on this chart, you see 14 subgroup averages. Those are subgroup averages. So this first point is X bar, X1 bar. The second point is X bar 2. The third one is the subgroup average of the third group, right? All right, so those points, which are the most critical elements on our variable chart, represent the subgroup averages. How about the lines that you see here? The most probably fundamental line you see here is the center line. So what is the center line and how it's calculated? The center line is the average of subgroup averages. So they are the averages of x1 bar, x2 bar, x3 bar, or x4, x5, x6, all of them. So we add all those subgroup averages and divide them by the number of subgroups. And this is going to give you the center line. And the way that we represent center line is x double bar. Now, this is something new. We knew what x bar means, but this is x double bar, which means average of all x bars. So basically, average of averages. So center line is the most important line here. The next most important line is the upper control limits and lower control limit. Upper and lower control limits are 3 sigma plus and 3 sigma minus points from your center line. So if we look at, if we look at a control distribution, a normal distribution, you have the average, right? And you have 3 sigma on this side to the right and 3 sigma to the left side. We know that for a normal distribution, the area between these 3 sigma values, that area is 99.7%. What does it mean? It means that almost all your data points in a normal distribution, all your data points are between 3 sigma plus and 3 sigma minus. Oh my God, what am I doing here? Minus and plus limit lines. So what is the relationship between this normal distribution and my variable control chart? If you remember from the first week, all subgroup averages are distributed normally. This is the result of central tendency theorem. So all subgroup averages are distributed normally. It doesn't matter what is the original distribution of individual values. When you look at the subgroup averages of any distribution, it is normally distributed. So this is always a control chart, always represents a normal distribution characteristic. So from this point, what I can say is, if I calculate the plus, this is upper control limit, so this is a plus 3 sigma and minus 3 sigma lines with respect to my center line, this chart is presenting 99.7% of all the data values. So again, what is the significance of calculating those plus and minus 3 sigma values? Again, let's remember 99.7% of all your data points should be between these 3 sigma plus and minus values. What happens if you find a subgroup average somewhere here outside the limits? It is a very, very small probability to find, right? It's less than 1%. So if you find a subgroup average outside those limit points, it clearly shows an out of control point. That's how important the limits are, all right? Because they are very powerful. It represents 99.7% of all the data points that you collect. And if you find a subgroup with an average, let's call it X bar, or the 15th subgroup, because so far we have 14 subgroups and this is going to be the 15th one. And if you find a 15th subgroup which is outside the plus and minus 3 sigma values, this is a very, very unlikely situation, and you can definitely say that something happened at this point in time. Something changed at this point in time that requires your attention. You have to go and analyze what happened, what changed at that point in time. Does that make sense? All right. So we have a variable control chart, which is an X bar chart that represents the subgroup averages. From subgroup averages, we calculate the X double bar, we calculate the upper control limits and lower control limits. We can easily calculate them, and we place our subgroup averages X bar 1, X bar 2, X bar 3, X bar 4, and then we try to identify patterns or outside the control limit points. And when we identify a pattern or outside the control limit points, we will say that that process is not under control. If there is no pattern or if there is no point outside the control limits, then we will say that this process is under control. All right. So this is basically the summary of what I have been talking about, how to create those variable control charts and what they represent. All right. So these are the same chart. All right. So how do we create a variable control chart? Now that's the most important thing we are going to do today. All right. We will create an X bar chart, and if we have more time left, we are going to also create an R chart. We have to create two charts. All right. This is the formula. Don't worry about it too much. This is the X double bar that I have been talking about. X double bar is the center line. Each individual point that you see is an X bar. First subgroup, second subgroup, third subgroup average, fourth subgroup average. Those are not individual readings. These are not individual observations. They represent subgroup averages, and the center line represents average of averages. So the X double bar is calculated from X bars. This is what basically this formula says. Here, M is the number of subgroups. And you just basically, sigma means that you add all the subgroup averages and then divide them by the number of subgroups. In our previous example here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, yeah, 14. In this case, M is 14, number of subgroups. Number of subgroups. If your subgroups have, let's say, 10 individual readings in them, and then let's say then n is equal to 10. N is the sample size or subgroup size or number of individual readings. Let's say you have the first subgroup, subgroup 1. So you have one reading, second reading, third reading, fourth reading, up to 10. All right. So number of subgroups and the subgroup size, those are two completely different things. And make sure that you use the correct parameter in the formula. Number of subgroups is represented by M, and the subgroup size or the sample size is represented by N. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14 subgroup averages we see here. Any questions up to this point? No questions? All right. So the next thing is calculating the upper control limits and lower control limits. As you remember, these are plus and minus 3 sigma lines from the center line. This is the formula. X double bar plus 3 sigma, X double bar minus 3 sigma. X double bar plus 3 sigma is going to be upper control limit. X double bar minus 3 sigma is going to be lower control limit. In statistical quality control, instead of using the sigmas, what we use is factors which are already calculated for certain situations with certain number of sample sizes. And that formula is transformed into this one, which is easier to calculate. Now, when you look at this, the new formula looks a little bit more confusing because now you have new parameters. What is A2 and what is R bar? The factor, which is A2, comes from a factor chart. This is the chart. It's available in your book, Appendix 2. Appendix 2, page 368. If you open that page in your book, you're going to find the same chart in your textbook. So as you see, you have your column for A2, which is used in that formula. So X double bar is a parameter that we are going to calculate. A2 is a factor that you will find from the chart. And what is R bar? R bar is the average of all the ranges for each subgroup. So what does it mean? If we look at this example, for example, you have 14 subgroups, and each subgroup will have a range, right? Let's consider the first subgroup. Let's assume that it has individual values like 5, 7, 4, 3, 1, right? These are the readings. I don't know what you were measuring, what you were really studying, but those are the readings. But okay, each subgroup has to be made of 10 individual readings. Let's do that. Oops. Let's create 10 individual readings. 2, 4, 7, 6, 5. How many? Yeah, we have 10 individual readings. So what's gonna be here is first from those 10 individual readings, we are gonna calculate X bar and we are gonna also calculate the range. What is the range? Range is the difference between the highest and lowest values. Here for this subgroup, the lowest value is 1 and the highest value, we have two of them, the highest value is 7. So what is the range? 7 minus 1, it is 6. So you have to do this for each subgroup. You have to calculate the range, and for each subgroup, you're going to have a range value, and that R bar value is the average of all those 14 ranges for our example. All right. So basically, all the parameters in this formula is either easy to calculate or already given in the chart, factors chart. Any questions? One more point. How do we figure out which A2 value am I going to use in this formula? It depends on the subgroup or sample size, N. All right, this is the sample size or subgroup size. So how many individual readings you make for each subgroup. In our example, as you remember, we said that we have 10 individual readings, 10 individual readings. So it means that your N is 10 here, right? So if we are considering the same example, first from the first column, you have to find N10, and that corresponding A2 value will be this value, 0.308. All right. So this chart is a very easy to use, very easy to read, as long as you know the sample size. Any questions up to this point? No questions. Now I'm going to go into an example problem. All right. There is no story given for this problem, just the numbers. But typically, when I ask a question, it is going to come in a story format. For example, I'm going to say that you're working on a production line and you are measuring such and such dimensions, and you collected 12 samples, 12 subgroups. All right. This is what it means. So subgroup number. Your M is going to be 12 in this case. And for each subgroup, you calculated the subgroup averages. Subgroup average. And also for each subgroup, you have calculated range. Subgroup range. And also, when you were collecting data, you did 5 individual readings for each subgroup. That's what N equals 5 means. N equals 5 means 5 individual readings. M12 means 12 subgroups. This is how you need to analyze the question. So, in the morning, you went to the production line, you have collected 5 parts, 5 pieces. You did 5 observations and you recorded them, and then you went to your office, and when you were in your office, you calculated the average for that first subgroup, which is made of 5 individual readings. And also you calculated the range for that subgroup. An hour later, you went back to production line, you picked 5 more parts or pieces or observations, you recorded them, you went to your office, again you did your calculations for that subgroup, you calculated the subgroup average, and you calculated the range. Okay? So this is how you create the table. But in our case, the subgroup averages and the ranges are already given to us to make our life easier. So what is the next thing to do? We want to create a control chart. I have copied the same values here. So from here, what I'm going to create is this chart, right? I'm going to create center line, upper control limits, and lower control limits, and I'm going to have subgroup averages. And the name of my chart is going to be X bar chart. Why do we call this X bar chart? Because we are going to place X bar values, those values on this chart. So let's start with the center line. Center line. Oh my God. Center line. How do we calculate the center line? Center line is the X double bar, which is the average of averages. So average of averages, we are going to use this column. We have to calculate the average of all these values. First, I need to calculate the total. What is the total of those values? Sigma X bar. I'm going to represent it like this. Sigma X bar is 4,184. And from that, X double bar is 4,184 divided by the number of subgroups, which is M, right? 4,184 divided by 12, and this is 348.7. So I just calculated the center line, which is X double bar. This value is 348.7. How about upper control limits and lower control limits? First, we need the formula. Upper control limit is X double bar plus A2 times R bar. Lower control limit is X double bar minus A2 times R bar. They are symmetrical because they are on both sides of our center line. So here we know X double bar, we can easily find A2. What we don't know is R bar. What is R bar? Average of ranges. Now we need to concentrate on the second column on our problem, the ranges. So first let's calculate the sigma ranges, right? Those are ranges, R values. What is the total of all the ranges? 164. And from here, what is R bar? What is R bar? R bar is all the sigma R values divided by the number of subgroups. So this is going to be 164 divided by 12. And this is going to be 13.7. So our R bar is 13.7. The last unknown in these two formulas of upper and lower control is A2. Let's find A2. A2 column is this one. So what we need to know is N. How many individual readings do I have in each subgroup? I have 5 individual readings in each subgroup. So here in this column, 5, here's my A2, and at their intersection, this is my A2 value. A2 is 0.577. Let's go back to our question and plug all the values that we know. I'm gonna write A2 value somewhere here, 0.577. Now let's plug in all the numbers we know and given. X double bar is 348. Oh my God, what's happening today? 347.48.7 plus 0.577 times R bar, which is 13.7. Lower control limit is just the symmetric of this, 0.577 times 13.7. And these values are 356.6, 340.8. So our upper control limit is 356.6 here. Lower control limit is 340.8. The last step is to place all the X bar values on our chart. So 340, it's the first one. Should be somewhere here. This is X bar 1. Then 347 should be somewhere here. This is X bar 2. The third one is 350, a little over the center line. Then 346, again 350, 45, 49, 48. Nope, this should be below here. Again 48, 54, which is going to be closer to upper control limit. 52, a little less than that, and 55. All right, so we have placed all our X bar values, subgroup averages on this chart. Do we see any pattern? Not really. Do we see any out of the control limit point? Not really. So how do we interpret this chart? We can easily say that this process is under control according to X bar values. All right. But this is not the only chart that we should create. This is only one of the 2 charts we have to create, X bar chart. The next chart we need to create is the R chart. In this case, in the first chart, we just analyzed the subgroup averages. We also need to analyze the subgroup ranges. All right. So how do we analyze the subgroup ranges? The same way, by creating a chart with upper and lower and center lines. And for this one, we have again a center line, which is basically the average of all the ranges. And we have upper control limit and lower control limits, which is D4 times R and D3 times R bar. Again, these D4 and D3 values are going to come from our factors chart. And R bar values. We already calculated R bar values. So let's go into creating an R chart. R chart. An R chart is gonna have center line, lower control limit, upper control limit. Lower control limit is gonna be, let's go, yeah, oops, where am I? Yeah, lower control limit is D3 times R bar, and upper control limit is D4 times R bar. So again, for each data, you have to create two charts, X bar and R chart. We already created the X bar chart. Now we are working on the R chart. Where is my R bar? We calculated our R bar here, right? R bar is 13.7. So this is already calculated. It's easy. Oops. 13.7. So for the lower and upper control limits, all I need to identify is D3 and D4 values. So my sample size is 5. So what is my D3? D3 is 0 and D4 is 2.114. D3 is 0, D4 is 2.114. D3 is 0, D4 is 2.114. Now let's plug all these numbers into our formula. Upper control limit, D4 times R bar. 2.114 times R bar. What is R bar? 13.7. Lower control limit, D3 times R bar. 0 times 13.7. And those values are 28.97. And this is, of course, 0. So this is 28.97, and this is 0. And the last step is we need those, range values, 13, 14, 12, 11. Oops. 13, 14, 12, 11, 15, 16, 14, 13, 16, 15, 16, 15, oops, I forgot it. 15, 16, 14, 13. Oops. 15, 16, 14, 13. 15, 16, 14, 13. Let's go back one more time. 12, 15, 13, 16. 12, 15, 16, 13, somewhere here. So these are the R values. The range of the first subgroup, the range of the second subgroup, those are R values. That's why we call it R chart. When we place all the R values on our chart, do we see any outside the control limit points? The answer is no. Do we see any significant pattern? No, we don't. So this is what we get by analyzing this chart. Um, Before we finish this, I'm gonna show you how to analyze the charts. What makes a pattern? What makes a process out of control? Obviously, if you find a point outside your control limits, it means that that process is out of control. So something happened at these points that needs to be identified, that you need to create a Six Sigma team, and that Six Sigma team is going to identify the problem there. Or, for example, something happened at this point in time, and the rest of the average values, as you see, present a trend. It's a decreasing trend. Again, you need to go back in time here and identify what went wrong. So it caused the system parameters to decrease. Here, all the data points after this certain point in time, it just shifted. We call it a shift, right? All the data points shifted. They are stable, but a shift happened. Maybe you changed an operator. Maybe a new material is introduced. Something happened. Here, what happens is all the data points is above or below the center line. Again, there is an unexpected and uncommon situation. So you need to, again, what is that time? You have to figure out and you need to identify what went wrong. This is also an uh, outside the control situation. A cycle that you see, the values are increasing and decreasing as a cyclic event. Maybe it's because of the most common reason is changes in temperature, because we know that early in the morning the temperature is usually low and then it starts increasing. At noon, maybe the highest, and then as the sun gets closer to the sunset, it will cool down again. So those temperature changes, cyclic temperature changes sometimes causes the expansion and reduction in the size of the materials, and those size changes can cause changes in the final product and final variations that you're analyzing. In this case, what we see here is the next reading is down and then goes up and down and then goes up and down. But more importantly, what's happening here is always it's one data up and then the next data goes down. It usually happens when you mix the data points from two populations. For example, you have two machines or two operators, and you get your first data point from the first operator, and then next time you go to the second operator and you get your readings from the second one. And the third time you go back to the first operator again, you get your readings. The fourth time when you come back, you go to the second operator and you keep doing the same thing. First operator, second operator, first operator, second operator, first operator, second operator. So it looks like a zigzag going up and down, but the main reason is you're mixing the readings from two operators or two machines or two systems or maybe two materials, and you shouldn't be doing that, because when you do that, you are not going to get correct averages that represents the process, because you're not analyzing one process. Actually, you're analyzing two processes, but you're mixing the values from two populations. And when you do that, you can see an out of control situation, and you shouldn't be doing that. So what happens when you see a pattern like this, or when you see an outside the control limit point like this one? You have to stop the production. You have to go back to that specific point in time, and you need to look for the changes, look for the problems, what happened in the past, and how to fix it. All right. After you fix it, you get rid of those data points and you create a revised chart. All right. So these are the steps. You interpret the original chart, you identify the cause of the problem, you fix it, and you revise the chart, you calculate the new charts with new formula. That's what we do in statistical quality control as part of the Six Sigma quality team.